So there are three parts of the course. The first part was, let's understand space, geometry and vectors, and we talked a little bit about parametric curves. Then we said, okay, well, let's look at differentiation, and how do we understand how things are changing. And the last part is integration. So integration is the part of calculus which asks the question, how much is there? And what's the total? So the way that we go about doing integration, and the philosophy, it's always the same. We say, okay, I'm going to break things up into small parts, small manageable parts. And each part, it's fairly easy to understand and get a good approximation on. So whenever I break things up, I have to make sure I break them up in a way that I can understand what each part is doing. And then I'm going to add all the parts back up together. And that'll be my answer. So when we had a function of a single variable, we say y equals f of x. One of the things we could do is we could find the total, which oftentimes we interpreted geometrically as being area under a curve. But again, integrals are not about areas. They're about totals. It's just the area gives us a way to visualize what's happening. So if I wanted to find the total, well, what we could do is we could split things up into little strips and say any one strip, I can think of this as being a rectangle. So I can find the area of a rectangle pretty easily. It's the height and the width. So what we do is we say, okay, we come to this interval. F of xi is the height. Delta xi is the width. This is the area of one little rectangle, and we add them all up. Now, when we go to functions of multivariables, so we're going to start with functions of two variables. So I have now z equals f of xy. So I don't have a curve, I have a surface. So I have this surface here, and it depends on where I'm at. And now, underneath here, I have a region. In this case, it's a nice square region. And what do we do? Well, previously we said, well, let's break it up into little parts. So now what we're going to do is we're going to break it up into little parts. Of course, now our little parts are little rectangles down here. So this little rectangle here, this is doing the same thing as this little length of strip here. So that's my change in my area, delta A, what we're calling it. Now I also need a height. Similarly as we're here, where I said, well, just plug a point in. Again, I plug a point in, and what I get is a height. So this f of xi, yj, that's the height here. Okay, so we take a height times an area, that's a volume, and so we can think of this as a way to find a volume underneath this surface. But again, integration is not about volumes, but one way to think about, sort of motivate our thinking, is as volumes. So that's our basic approach. Now, if we think about these as sums, these are called the Riemann sums, and not to be confused with Riemann, which is something different, the Riemann gardens. So for the Riemann sums, well, how do you get a better approximation? Well, the answer is, of course, you go and you split your interval up into smaller parts. So the smaller the parts, the better the approximation will be. And that's sort of the magic of calculus, is saying, look, as I make things smaller and smaller, the approximations at each part get better and better. And so when I add it up, the total approximation gets better and better. So that's what we want to have. So what we do is we look at the limit as the size of our parts gets small, and you can tell we're really waving our hands here because we're just sort of using English. That's when you know you're doing really advanced math, when they start using English. So this is going to be what we call the integral. And when this limit exists, we denote this with the following. The integral over our region. And notice that there's two integral signs, f of xy dA. Now, why are there two integral signs? Well, because it's a two-dimensional integral. So the number of integral signs should match with the dimension of what it is you're trying to integrate. So if it's over a two-dimensional region, so when we say a dimensional region, the domain, if our domain is two-dimensional and we're integrating over our domain, we'd put two integral signs. Later on, we'll get to three-dimensional integrals, and we'll have a third integral sign. Whoa. All right. Now, how do we know when something is differentiable? Well, that's tricky, but the good news for us is that there's a case where it's always going to be, sorry if I said differentiable, I should have said integrable. There's something where it's always going to be integrable, and that's if our function is continuous. So the good news is nice functions are integrable. And we're only going to deal with nice functions. So now we actually want to talk about, well, how do we go about doing the integral? Because you can probably guess we don't want to do it by the definition as the limit of sums. No, that would be not good. Oh, that's also not good. Wake up. Okay, there we go. All right. So let's establish a couple of basic results. And hopefully none of these are too surprising. Okay, so here we go. If I integrate 1 over my region, I'll get the area of the region. Now that makes sense. Because if we go back and look at their definition here, if I'm integrating 1, so this function is 1, then what I'm really adding up is how much area is in that little piece. So what I've done is I've broken my area up into lots of little pieces. I said, well, how much area is in that piece? How much in that one? How much in that one? And I'm adding them all together, and that'll be the total area. Okay, so that's not a surprise. The next one says if I have a constant, so I'm integrating a constant times f of xy, I can pull the constant out of the integral. Now that one also makes sense. In fact, let me say that there's two of them that go together. The next one says if I'm adding two things integrating the sum of two things, f plus g, I can integrate just f, and then I can integrate just g, and I add the results together. Now these two things together, the fact that we can pull out the constants and the fact that we can separate our sums, integral of f plus integral of g, is a reflection of the following, that integration works really well with addition. Because integration at the end of the day is all about adding things up. And once you understand that that's what integration does, you say, well, of course I can pull out constants, because if all my terms in my addition have a constant, I'll just pull that constant out. And if I'm adding things together, if I'm adding a bunch of things which are added, I can rearrange my terms. So integration works really well with addition. That's the moral of the story. Now, another thing we have is it respects inequalities. So if I have that f is bounded above by g, so I have this how can we visualize this? Well, so I have here is my space, and then I have some surface here. Here's my f, and then somewhere above it I have a g. Then I can say that the total volume, if I'm thinking in terms of volume, that's under g is more than the volume that's under f. Okay, well that's not so hard to see if you think about it in terms of volume. If you think about it in terms of sum, you just say, oh, look, the individual pieces satisfy my inequalities, and therefore they all do. And then the last part is a nice result that says, hey, let me turn that. It says, if I'm working with something, and my region I can break into parts, so for example, I can take my large rectangle, and I can break it into two small rectangles, then the integral over the large rectangle is the sum of the first rectangle plus the sum of the second rectangle. So in other words, I can take my region and I can break it into parts as I need. Now why would I want to break it into parts? Well, it might be that my function is a piecewise function. So that over R1, it has one definition, but over R2, it has a different definition. And so if I break into parts, then I'm able to handle them in separate ways, and life is good. It also might be the case, of course, I want to glue things together. I might have, here's an integral over one piece, here's an integral over another piece. Let me put them, make an integral over the two pieces combined. And that can, in some cases, make things easier. So, let's try a problem. So let R be the region where x goes between 0 and 2 and y goes between 1 and 4. Now, we can write this as 0, 2 cross 1, 4. So you think of this 0, 2 as indicating what's happening with your first variable. So we usually think of our first variable as x. 1, 4, that's an interval saying what happens with your second variable. It goes between 1 and 4. So this is something we could probably sketch. So here's 0 to 2. We're going there in the x direction. 1 to 4 in the y direction. So our region, it's a nice rectangle-like region. So given that the integral over this region here, R, so I guess we should label this, here's R, of f of x, y, dA is 7, we'll find the integral over R of 3 times f of x, y minus 4. And then, of course, we have the dA. Now, right now, we don't have very many tools. Well, that's good. The fewer tools you have, then that makes it easier to figure out what you have to do. So what are some things we can do? Well, we'd like to pull a constant out, but what's something we should do before we pull a constant out? Yeah, we could try first breaking it up. So if we use the fact that I really have two things, now you might say that's a minus, that's not a plus. Well, I can think of this as a plus a negative 4. Because really subtraction is just adding a negative number. So I can say, okay, I can say that my integral over my region, 3f of xy plus negative 4 dA, I can break it up into two pieces. The integral region of 3 f of xy dA plus the integral over my region of negative 4 dA. Now pull out a constant. What constant do we put out of the first one? 3. 3 over our integral over our region, f of xy. What do we pull out of the second one? Negative 4. So it'll become minus 4, integral over our region, dA. Well, what happens to the first piece? So the integral of our region, f of xy dA. Well, oh, yeah, it was told to us. That's 7. Minus 4. What happens to this piece? It's the area. Because if we integrate 1, we get the area of the region. Well, how much area is there? It's 2 wide, 3 high, so the area is 2 times 3 gives us 6. So 21 minus 24, which is negative 3. Now, is it okay that we got a negative number? Yeah, it's okay. See, integrals are allowed to be negative because the integrals are representing totals, and sometimes totals might be negative. Now, depending on the problem, if you're looking for something which is a measurement of a geometrical thing like a volume, and you got a negative volume, you'd be concerned. But it's okay that we got a negative number. It's kind of like a bank account. Yeah, sometimes bank accounts go negative, but that's okay. Maybe. All right. So, how do we actually do this, though? I mean, we want to get something a little bit easier to work with. So, okay. So here's what we're going to do. So we layer things on. So I have here my surface. So here's my surface. This is my z is the function of x and y. I'm going in the x direction between a and b, And in the y direction, I'm going between C and D. So here's my domain. Now, our basic idea that we had was, let's break things into pieces. Okay. So in particular, more or less the idea was like, let's just chop up our domain into little tiny rectangles and work with the rectangles individually. A better idea, and this is where we're going to go, is not to break things into pieces, but to really break things into strips. So it's like we're slicing. So you can see here, we've sliced in two different ways. So we've taken a slice where I'm holding my x fixed, and I get a little blue slice, or where we hold the y fixed and we get this little red slice here. Now, why is that useful? Well, if we look at a slice, we can say, hey, that looks a lot like just a function of a single variable. And we are a little bit more comfortable with how to do things with functions of single variables. So as an example here, if I hold the y value fixed, so this is the y value fixed, it's the red one here, then what I see is when I look at that cross-section, I get the shape that goes between x equals a and x equals b. So I'm going from a to b, and I can say, well, the area of the cross-section is the integral from a to b of f of xy dx. Now if I want to find the volume, or the total, well, what I can do is I can say, well, it's the area times a little bit of change in y. I'll call that delta y. So what does that? Well, the area, we just plug in what we just found. It's the integral from a to b of f of xy dx. And then we're adding up delta y. Well, now we take our limit, delta y gets smaller and smaller, and that becomes an integral. Y is going from c to d, integral a to b f of xy dx dy. Of course, alternatively, we could have held x fixed. So if we had held x fixed, what would have happened here is we would have gone this blue slice. So here's the blue slice. Notice that y is going from c to d. So that the area of the cross-section for a particular value of x, it's the integral from c to d of f of xy dy. So again, the volume, that's the sum of the area times a bit of delta x, and lo and behold, it becomes an integral of an integral. So what we have now is really a series of nested integrals. And you have to be a little bit careful here, just to remember that when you're integrating, for example here, when we're integrating, what are we integrating with respect to? We're integrating with respect to the y. What do we do with the x? We treat them as constants. And the reason we treat it as constant is because we're holding x fixed. We're like working in a slice, so x is fixed. So these are what we call iterated integrals, where we integrate one variable at a time. Now, how do we actually do these? Well, you work from the inside out. So you start on their innermost integral, evaluate that, then you go to the next layer and evaluate that. And we might have multiple layers. We keep going. And the important thing is when you're integrating with respect to one variable, you treat the other variable or maybe other variables as constant. So this is a time when we say that notation is important. We really were after in Calc 1 and Calc 2 said, look, you've got to pay attention to notation. You've got to pay attention to notation. And now this is why. Because notation is giving you instructions on what to do. So if I write down the integral from c to d, integral from a to b of f of xy, and I didn't tell you dx dy, then you don't know how do you proceed. Because the question is, well, which integral is associated with x and which integral is associated with y? So you need the dx dy. That's really important. So that's why we kept saying notation, notation. It's going to be important. Because that's today. Finally, after all this time, it's like, oh, that's why they care. Not just because they want to take points off, but because they want us to be able to answer questions. Good. Now, how do you read off the notation? Well, you always pair things up. So the inner integral goes with the inner dx. The outer integral goes with the outer dy. In this case, it might be the other way around. And oftentimes we do shorthand. See how we go a to b? But really that stands for something, because this a to b is associated with the dx. It really stands for x equals a to x equals b. And similarly, this c to d, that's associated with the dy, and it means from y equals c to y equals d. Once you understand the notation, it becomes a lot easier to work with the integrals. All right. So let's try this out. Find the volume between the surface z equals xy squared and the xy plane for the region R, which consists of x going between 1 and 3 and y going between 0 and 3. So, what do? Well, our region here, it's a pretty simple region, goes from 1 to 3 and 0 up to 3. So there's our region. Now there's a choice that has to be made. And that is to say, how do you go about slicing? Because if you go back to your picture here, notice we can slice in two different ways. So essentially the question is, are we going to integrate first with respect to x, then y, or do we integrate first with respect to y, and then x? Well, what do you want to do? X, then y, or y, then x? Well, okay, let's start x, then y. So we're going to integrate the function we're integrating, that's the height. So that's xy squared, and then dx dy. So to figure out the bounds, you say, okay, where does y go between? Well, it goes from 0 to 3. Where does x go between 1 to 3? So we now work this out. So we're back to our kind of our onion problems. We got layers. You got to work through the layers one layer at a time, and hopefully not too many tears now. We'll save those for later. When I integrate xy squared with respect to x, what do we get? Well, if I integrate xy squared, the y squared is going to stay y squared. What happens to the x? 1/2 x squared. 1/2 x squared y squared, going from, and now I'm going to be really careful with the notation. Normally we would just write 1/3, but I want to emphasize I know what I'm evaluating. So I'm going to write x equals 1 to x equals 3. So I remember that it's the x's that are being evaluated. Okay, so this will become integral from 0 to 3. Plug in x equals 3, that's going to be 9/2 y squared. Subtract, plug in 1, that'll be 1/2 y squared dy. And if you evaluate that, well, 9/2 minus 1/2 is 8/2, so that's 4y squared. Okay, now we integrate with respect to y. What's the integral of 4y squared with respect to y? 4/3 y cubed. Going from y equals 0 to y equals 3. Again, I'm going to just really emphasize I know what I'm evaluating. So I'll put in y equals 0 to y equals 3. Even though at this stage I know there's only one variable involved. So if we plug in 3, we get 4/3 times 3 cubed, which is 4/3 times 27, which gives us 36. If I plug in 0, we get 0. So the answer is 36. Well, that didn't take a lot of space. Well, since we have so much space, let's do it the other way. All right, what's the other way? Well, the other way would be if we did xy squared dy dx. Well, where does x go between? X goes between 1 and 3. So that's my outer bounds. Those are my x bounds. The inner bounds are the y bounds. Where does y go from? 0 to 3. So we work our way through the process. If I integrate with respect to y, because my inside integral, again, we think of these as just one at a time. My inside integral is with respect to y. What's the integral of xy squared with respect to y? 1/3 x y cubed. And then we're going to evaluate from y equals 0 to y equals 3. So we plug in 3. Well, we'll end up getting 3 cubed is 27 times 1/3 is 9, so we'll get 9x. We plug in 0, we'll get 0. 0 is a good number. We like 0. Okay. Integral of 9x? 9/2 x squared. Then evaluate x equals 1 to x equals 3. Well, we plug in 3, we're going to get 3 squared is 9, so we're going to get 81 over 2. Then we're going to subtract, plug in 1, 9 over 2. Now 81 over 2, subtract 9 over 2, that's 72 over 2, also known as 36. Oh! We got the same answer. Is that surprising? No! In fact, it's very expected because we're looking for the same thing. In both cases, we were expecting to get, in both cases, we were computing what's the volume. And the volume doesn't change based on how we compute it. And so it should have been the same answer. But you'll notice that even though the volume didn't change, sort of our intermediate steps are different. So, these two integrals, if you just saw them, it's not immediately obvious that you should have gotten the same value. So your intermediate work will look different, but your final answer will be the same. All right. So what we get here is that this is an example. If I have a rectangle, I can really integrate it in either way. So a to b, c to d, if I'm integrating first with respect to y, then with respect to x, or c to d, then a to b, integrating first with respect to x, then with respect to y. So it's possible to change the order of integration. Now, you might say, okay, it's possible, but why would we do that? Well, changing the order of integration might actually make things simpler, depending on the problem. So there are situations where if you integrate in a certain order, it can either be very, very easy or very, very impossible. And we prefer the very, very easy. So be aware that changing might be important. In fact, that's going to be a big thing that we're going to do. There's not going to be a lot of new integration techniques that you're going to learn. It's the same functions that you learned back in Calc 1. We're almost never going to do anything from Calc 2. So there's nothing new when it comes to doing the actual integration. The big thing right now for the next couple of weeks is learning how to set things up. And for that, we have to understand things like the bounds. That's going to be a really big part. So we'll do some examples. We'll do some examples to illustrate this principle here. Here's a simple integral. Maybe. Find the integral from -5 to +5 of the integral from 6 to 27 of arctangent y to the 6 sine of x to the 53rd power dy dx. So we want to find the answer to this. Okay. So as the integral is given to us right now, what do we have to do? We'd have to integrate with respect to what? We have to integrate with respect to y because the inner layer is with respect to y. And the reason the inner layer is with respect to y is because we can really pull off the inner layer that goes with the inner dy. So if I'm integrating with respect to y, right now I don't worry about this part with the x. I'd have to integrate arctangent of y to the 6. Can we integrate arctangent y to the 6? Yeah, but we don't want to. Oh my gosh, that almost makes me want to. But I don't want to. That does not look like a pleasant integral. So I say, okay, though that's not a pleasant integral. So what can we do? Yeah, we can change the order of integration, because that's what we just talked about. I was talking about, let's think about the changing the order. So if we flip the order, now because it's a nice square region, because if you look at it, it says x goes from -5 to 5, y goes from 6 to 27. That means we're integrating over, well, not square, but a rectangle. But okay, so changing the order for rectangles is very easy. So 6 to 27, -5 to 5, and still the same function. So when you change the bounds, you don't change the function, you're just changing the way you're describing the region. In essence, that's what's happened. Is you can think about the bounds are describing the region for you. So currently, the way that the region was described, well, in the initial problem I said, well, y is going to go from 6 to 27, and then x is going to go from -5 to 5. We flipped it and said, well, x is going to go from -5 to 5, and y is going to go from 6 to 27. Okay, well, is it better now? I mean, we don't have to integrate arctangent y to the 6. That's the good news. Now what do we have to integrate? Sine of x to the 53. Ah, that feels so much better. Or does it? Well, sine of x to the 53. I mean, if we were back in Calc 1, we'd say maybe it's just like cosine of x to the 54 or something over 50. No, that doesn't work. Sine of x to 53, it's a very weird function, very peculiar. It's unusual. Not the kind of function you see every day. It's strange. We might even say that this function is odd. Okay. It's an odd function. What do we mean by an odd function? So an odd function is one where if you plug in -x, what do you get? It's negative of if you've plugged in positive x. And so in particular, an odd function is something which has symmetry that looks like this. Now, the beautiful thing about odd functions when it comes to integration is it so happens if you integrate from, say, positive a to negative a, if you integrate this region versus that region, how do they compare? They're equal in size, but they're different in sign, so they cancel out. It's like area and anti-area, and they collide with each other in a beautiful mathematical explosion, and we're left with nothing. All right, so the area cancel out. Now, in order for us to use this, we'd have to say, do the bounds have that form -a to a? Well, they do. Now, you might say, but wait a second, what about this arctangent y to the 6? What happens there? It's acting like a constant. In fact, one of the things that you can do is if you wanted to, you could even pull it out. Because it's a constant, I could really think of this as arctangent y to the 6 as being pulled out of this integral. So this, I can pull out of the inner integral because it's a constant, integral from -5 to 5 of sine of x to the 53 dx dy. But now by symmetry, this integral equals 0, which means that we integrate from 6 to 27 of 0, and that's one we can do, giving us a final answer of 0. All right. Well, let's try another one. Let R be the region where x goes between 0 and 2, and y goes between 0 and 2. Okay, so it's a nice rectangle, and we want to integrate with over our region R, x e to the xy dA. All right. Well, that doesn't sound so bad. Now, when we're asked to integrate, the only way we're going to integrate, if we actually have to, is iterated integrals. That's the only technique we're going to learn when it comes to integration. Is to say, okay, how do we work it as an iterated integral? So we have to set this up as an iterated integral. So we have two choices. So the first choice is to say, all right, we're going to integrate e to the xy, that's our function, x e to the xy, excuse me. And then we're going to integrate that dx dy, or we're going to integrate x e to the xy dy dx. Now we have to get our bounds. So where does y go between 0 and 2? And where does x go between 0 and 2? All right, x goes between 0 and 2, and y goes between 0 and 2. Okay, so life is not so bad. Okay, so that's our choice. Well, it doesn't matter. We're going to get the same answer either way. So let's do the first one. Integrate dx dy. Okay, so suppose we had to integrate this. We have the integral x e to the xy dx dy. So how do you work the inner integral? What technique do you need? It'd have to be integration by parts, because you have an x times e to the xy. Well, we know integration by parts, I think. Should we? Yeah, we can do integration by parts. We've got a few minutes. We can figure this out. So if we're integrating x e to the xy dx, so this part, well, that's would be great if we take the derivative of that because it makes it easier. So that means we're going to integrate this part. So our du would be dx, and what's the integral of e to the xy with respect to x? 1 over y, e to the xy. So this would become uv, so that would be x over y, e to the xy. And then we're going to subtract the integral v du. So 1 over y, e to the xy, dx. So that's x over y, e to the xy. Now if we integrate this, well, the 1 over y, again, it's a constant, and the integral of e to the xy would produce another 1 over y, so it becomes minus 1 over y squared, e to the xy, and then plus the c. So that's if you were doing an indefinite integral. So that says that this becomes, and I'm just going to copy what we have here, x over y, e to the xy, minus 1 over y squared, e to the xy. And I don't need the c anymore because I'm going to evaluate x equals 0 to x equals 2 dy. Okay, that wasn't so bad. Why were we nervous? So now we plug in x equals 2. 2 over y, e to the 2y, minus 1 over y squared, e to the 2y, subtract, plug in 0, haha, 0, that's nice, that term goes away, minus 1 over y squared, and e to the 0, that term becomes 1. And all that is being integrated dy, which means that we have the integral from 0 to 2 of 2 over y, e to the 2y, minus 1 over y squared, e to the 2y, plus 1 over y squared dy. And all we have to do is integrate that. Okay, so how do you integrate 2 over y, e to the 2y? Oh, integration by parts actually won't work on this one. Because no matter what you do, if you differentiate 2 over y, you start getting bigger powers of y downstairs. if you try to integrate 2 over y, what do you end up with? Natural log of y. If you integrate that, then you end up with a headache. You know, so integration by parts won't do it. In fact, you're stuck. You can't integrate that. Oh man, but we wanted an answer. That kind of bummer. But wait a second. We made a choice. Apparently, we chose poorly because we got kind of stuck. See, we said, well, it doesn't matter. Apparently, it could matter. You should make good choices. I feel like this is an after-school special now. Okay, so maybe we shouldn't have integrated first with respect to x. Let's go back and cover this all up and integrate first with respect to y. Okay, can we integrate x e to the xy with respect to y? Now the nice thing is, previously when we were integrating with respect to x, we had to use the product rule. Do we need the product rule here? No, because x is acting like a constant. So it's like I have this constant e to a constant times y. So what's the antiderivative of e of, well, let's say x e to the xy, antiderivative with respect to y? It would be e to the xy. And then we're going to evaluate from, in this we're doing the y, so y equals 0 to y equals 2. All right. So if we evaluate, we're going to get e to the 2x minus e to the x times 0, which is e to the 0, which is 1. Now, that feels like a much better integral for us to do. What's the integral of e to the 2x? E to the 2x over 2. What's the integral of minus 1? Minus x. And then we're going to evaluate from 0 to 2. So we plug stuff in. Plug in 2. We get e to the 2 times 2, which is e to the 4th, divided by 2. Subtract 2. If we plug in 0, what do we get? Well, we're going to get e to the 0, which is not 0, it's 1. So we get a half and minus 0. And we can clean this up a little bit more, because we can say minus 2 minus a half is minus 5 halves. So we end up with 1 half e to the 4th, subtract 5 halves. And that's the answer. Which also tells us that if we were able to integrate this, which we can't, but if we were, so we could say, you know, a miracle happens, and what ends up happening is that this would have to be 1 half e to the 4th minus 5 halves. Because we have to get the same answer. It has to be consistent. So even though we can't integrate this, whatever it, if we could, that would be what the answer would turn out to be. Now you might object a little bit and say, but Steve, that integral is a little bit improper. Just a little bit. We can fix it. Do limits, it works out. Okay. So, last thing to mention for today. There's a sometimes useful fact. If it's the case, you have the following. All the bounds are numbers, which really says I'm integrating over, say, a rectangle, or once we get up to 3 variables, integrating over a box. If all the bounds are numbers, and the functions you're integrating are easy to split apart. So by easy to split apart, we mean f of xy is really a function of x times a function of y. Then it turns out that you can really pull apart the integrals and do them separately. So that is to say that the integral from a to b, integral c to d of g of x times h of y dy dx is the integral from a to b of g of x dx, integral c to d of h of y dy. The reason why it works is actually a really simple idea. So look at this integral here. The inner layer, what are you integrating with respect to? We're integrating with respect to y, because there's that dy. So how do you treat this g of x? It's a constant, and if it's a constant, we're allowed to pull constants out of integrals. So that's how we get from the first step to the second step. It says, hey, we're allowed to pull constants out of integrals. But now look at this integral. What is this going to be? It's going to be a constant. It's whatever the integral turns out to be. And what are we allowed to do with constants? We're allowed to pull them out of integrals. I just pulled it out of the backside in this case. So it's the idea that you can pull constants out of integrals that allows you to separate these integrals into pieces. So be careful. You really need to make sure that the bounds are always numbers. You might say, they're always numbers today, but there's always tomorrow. Oh yeah, things are going to get a lot more interesting next time. So be careful. It doesn't always work. The other thing is your function has to be that kind of function, a function of x times a function of y. If it's not, it doesn't work. So suppose you're asked to find the following. Our last example for today. Integral from 0 to pi, integral 0 to log 2. Sine of x e to the y minus y sine of x dy dx. Now, we're not quite of the right form. Function of x times function of y. But what can you do to this expression? You can factor sine of x out. So sine of x e to the y minus y. And now I say, okay, here's my x part, here's my y part. So I can separate. So the x part goes from 0 to pi. So 0 to pi, sine of x. My y part, that's the inner layer, 0 to log 2. E to the y minus y, dy. So again, this is going to be two integrals multiplied together. We can do them separately. What's the integral of sine? Negative cosine. We're going to go from 0 to pi. What's the integral of e to the y minus y? Again, with respect to y. E to the y minus a half y squared. All right, and we're going to go from 0 to log 2. So, minus cosine of pi, minus cosine of 0. Well, minus cosine of 0, so that's plus cosine of 0. Over here, we're going to get e to the log of 2 minus 1/2 log of 2 squared. Subtract e to the 0 minus 1/2 0 squared. Okay, minus cosine pi. That'll turn out to be 1. Plus another 1 says that this part becomes 2. Now e to the log 2 is 2. E to the 0 is 1. So these two terms are going to combine together. The 0 squared goes away. And 1/2 log 2 squared. How can you write that? As 1/2 log of 2 squared. Yeah, you can't write that any different way. That's what it is. So our final answer is 2 times, and here we have 2 minus 1, which is 1 minus 1/2 log of 2 squared. So this sometimes saves just a little bit of work. It's something which you'll see me do from time to time when I'm in a rush. And that's it for today. We'll see you next time.